In this video, I'll be talking about our work on approximating kernels with Gaussian Quadrature. We developed a new method to deterministically approximate kernel feature maps. To guarantee error less than epsilon, the popular random Fourier features method requires a large number of features, quadratic, in 1 over epsilon, while we need way fewer features, scaling almost logarithmic in 1 over epsilon. Our method works particularly well with a class of kernels called sparse ANOVA kernels. And in the domain of speech recognition, our method yields competitive performance. Kernel methods have gained resurgent interest, as comparing deep learning and kernels help us understand why deep neural networks work better than classical methods. Recall that a kernel function k encodes similarity between data points x and y. It is also the inner product of some implicit feature map phi x and phi y. However, the feature map is usually infinite dimensional. For computational reason, we approximate phi with phi tilde, a finite dimensional feature map. We can then apply off-the-shelf linear SVM or logistic regression on top of these features. Prior methods of kernel approximation mostly use random feature maps. The use of randomness means that to achieve a small error epsilon, we need a large number of features on the order of 1 over epsilon squared. The natural question is, can we remove randomness in kernel approximation? It turns out that we can. In the case of shift invariant kernels, by Fourier inversion, we can write the kernel kx minus y as an integral of the kernel spectrum, here denoted by lambda, with omega being the frequency variable. Approximating this integral by finite sums yields an approximate feature map, and the kernel approximation error is exactly the integral approximation error. Approximation by random sampling yields the popular random Fourier features. Another method to approximate integrals is Gaussian Quadrature, which has been used for decades to numerically solve PDEs. If you use Gaussian Quadrature here, you'll get deterministic features. We showed that you need way fewer deterministic features to achieve the same error epsilon. The number of features scales by a small power of 1 over epsilon, compared to 1 over epsilon squared of random Fourier features. However, we scale exponentially with respect to the dimension d. This is great for low dimension, but the exponential dependence on d seems to be a killer. There is one class of kernels for which deterministic features work well. They're called sparse ANOVA kernels, or convolutional kernels. They have low effective dimension, and they're used widely in speech and images. The kernel is the sum of small subkernels, each acting on a small subset S of indices. The subset S captures the local interaction between covariates, like a convolutional layer of a CNN. For this class of kernels, our method scales linearly with respect to the kernel size m, which is the number of subkernels, while random Fourier features method is cubic in m. Our dependence on the error epsilon is again much better as well, scaling by a small power of 1 over epsilon. We tested variants of our method on TIMIT, a speech recognition dataset. When we combine our method with subsampling and reweighting, we get much better kernel approximation error compared to random Fourier features and quasi-Monte Carlo methods, as shown on the left plot, where our methods are the dashed lines. Our downstream performance, measured by phoneme error rate, is also better, as shown on the right. In summary, the Gaussian Quadrature approximation requires way fewer features and works well with sparse ANOVA kernels due to their low effective dimension. Besides speech recognition, we're excited to apply these techniques to settings where CNNs have found success, such as in image processing, sentiment analysis, and machine translation. We hope that our work will help kernel methods scale to large datasets in these domains as well. Thank you for your attention. Be sure to check out our poster at NIPS.